Hi Level 3s, welcome back to 3.6 Aqueous Chemistry. This is Lesson 7 Part B, the final part of this video. We had just solved this problem here, talking about how the solubility of calcium carbonate in water was 5.74 times 10 to the negative 5. And then we calculated the solubility inside a solution of a common ion, and that was in a solution of sodium carbonate. And so in water, that number was 5.75 times 10 to the negative 5 moles per litre. And so what you can actually see is that this number here in water is far, far greater than the number in than the concentration in sodium carbonate. So you can actually see the solubility has decreased when it's been put in a common ion. And that matches all of our theory of Le Chatelier's principle, where I'll just go through it one more time. Here's the equilibrium that we're dealing with. So if the concentration of carbonate goes up, the equilibrium will automatically shift to do the opposite, so it'll shift to decrease the concentration of carbonate ions. It'll always do that by shifting to the left, and if it shifts to the left, you're going to get more of the calcium carbonate solid, and therefore solubility has decreased. And so therefore we have just mathematically shown what we have theoretically predicted using that principle. So it's really, really cool. So here's a bit of a harder example, but we'll just keep doing examples. I think we're doing a total of 6. So magnesium hydroxide is a substance that patients consume to control acid reflux. And so here is the solubility product of magnesium hydroxide. It says calculate the solubility in water, so that's just normal. And then it says what is the concentration of Mg2 plus ions in a 0.15 mole solution of sodium hydroxide. So we'll talk about that second part in just a second. Let's just focus on the first part. Whenever you're given one of these questions, the very first thing that you should always do is do a nice balanced equation including states. So magnesium hydroxide solid forms magnesium ions aqueous plus 2 hydroxide ions aqueous. Okay, so remember, when you're calculating solubility, you are calculating X and it's a concentration. You can see you've got 1 magnesium ion for every 2 hydroxide ions, so this is a 1:2 ratio. We've been given no masses or anything like that, which means that we know that we have to solve for X. And so this, if you look here, we can now do a Ks. Ks equals products divided by reactants. So you've got magnesium 2 plus OH minus squared. 1x for magnesium and 2x squared for hydroxide, because there's twice the concentration of hydroxide ions. So if we expand those brackets, you end up with 4x cubed, okay, and that's Ks. So if we're trying to find solubility, which we know is solving for X is going to equal the cubed root of your Ks divided by 4. And I'll show you the working now. So here we go. So we've got exactly that. X equals 1.46 times 10 to the negative 4, and the units are moles per litre for solubility because it's how much can dissolve. So let's go back to the question to make sure we've understood. So the next question is, calculate the concentration of magnesium ions in a 0.150 mole solution of sodium hydroxide. Okay, so it's if they put, what they're saying is, if we put magnesium hydroxide into a 0.150 mole solution of sodium hydroxide, what's the concentration of magnesium ions? Okay, so it's still this magnesium hydroxide equilibrium, but it's been put into a solution with common ion. So what's common between magnesium hydroxide and sodium hydroxide? It's the hydroxides. So that's what we're going to do. They've given you the concentration. Remember, this concentration of hydroxide is going to be far greater than the concentration of hydroxide produced from our equilibrium. So we're just going to use that concentration. They said, so here's the answer. They said 0.150 mole per litre of sodium hydroxide. Sodium and hydroxide are in a 1:1 ratio, so that means the concentration of sodium is 0.150 and the concentration of hydroxide is 0.150. We don't actually care about sodium in this instance, but I just always do that every time, just to make sure you're clear with what's going on. We're solving for X today, and we're going to use the concentration of the common ion here. So basically a shorthand thing is that the concentration given for a common ion question is the concentration you use. We've already worked out our Ks expression from the last part. So we have got a Ks and we've got a hydroxide concentration. So now we're just rearranging for the magnesium concentration. So you've got your Ks, you've got your hydroxide. Okay, we square it and there's the answer here. Now there's one key difference here that I'm hoping some of you have picked up. You will notice I have not 2x'd this concentration. And the reason why is because this is the concentration of hydroxide. This was given to us. They said the concentration of the solution that you're putting it in is 0.150 sodium hydroxide. And so that means the hydroxide concentration is this concentration. So we don't need to times it by 2 because that is the concentration of hydroxide. I hope that makes sense. And your answer should always have the units moles per litre. Okay, so we're going to do a slightly harder example now. So this one's calculating the solubility. Remember, solubility is solving for X of lead chloride in a 0.5 mole per litre solution of calcium chloride. Okay, and the equilibrium's been has been kindly given to you in this question. So it says calculate the solubility of lead chloride in a 0.5 mole solution of calcium chloride. So where kids automatically go a bit wrong in this question is the fact that calcium chloride, okay, so CaCl2 is a 1:2 ratio. So if you've got 0.5 calcium chloride, that means that calcium's concentration is 0.5 and chloride's concentration is 0.1. Okay, so that's the big thing there. So calcium and chloride have got different concentrations, and so that's what you've got to account for as you start this process. So what's our common ion? So which, in calcium chloride, what's common between that and lead chloride? And obviously it's the chloride ions. Okay, so we're going to use this concentration of chloride ions to complete our question. Okay, so just don't forget that's going to be the 1 mole per litre. So we just do as we normally do. So Ks equals Ca2 plus Cl minus squared. Okay, we've got a Ks. The Ks was given to you in the question. It's 6.81 times 10 to the negative 5. We've got a chloride concentration. It's 0.1. We just use that concentration. So we just rearrange to solve for X, and X equals 6.81 times 10 to the negative 5 moles per litre. So I hope that makes sense. You'll see up here I've put S. S is the same as X. So sometimes when you look at NZQA exams, you'll see the mark scheme says S equals. That's just saying solubility equals, and so you can put X equals or S equals. It's fine either way. Okay, task 6, and I believe this is the last one for today. This is actually a discussion-based one, not necessarily calculation-based down the bottom. So it says sufficient silver chromate is dissolved in water to form a saturated solution. Just making sure we're recapping here. Saturated means no more can dissolve, and that is when you've reached equilibrium. Okay, write the equation for the equilibrium present in a saturated solution. So nice and simple, we always start with the solid. Equilibrium arrows 2Ag plus aqueous plus CrO42 minus aqueous. So that's your equation. You write the Ks expression, so Ks equals Ag plus squared and CrO4 minus, like so. And now it says calculate the solubility in a saturated solution. Okay, that couldn't be easier. That's just in water, so it's your normal. This is a 2x and x, so therefore Ks equals 4x cubed, and you rearrange to solve for x. So I'll flick to the next slide so we can just look at that. Okay, exactly as we said, and x equals 9.09 times 10 to the negative 5, and it's moles per litre. Please be mindful, NZQA expect you to do everything to 3 significant figures. Okay, so that's really important. Okay, this next question is a discuss. It says discuss how the solubility of silver chromate will change if it's dissolved in the following solutions. So the first is if we dissolve it in potassium chromate. Now hopefully you'll see if we've got silver chromate and we dissolve in potassium chromate, chromate is common to both, so this is a common ion problem. Okay, so we'll quickly answer this now. So here's our equilibrium up here. Okay, if we increase the concentration of chromate, CrO42 minus, oops, I'll just redo that, it was a bit messy. If we increase the concentration of CrO42 minus, the equilibrium is going to shift to decrease the concentration of CrO42 minus. How will it do that? It's going to shift to the left. So the equilibrium will shift to the left. You'll get more Ag2CrO4 solid, which means solubility is going to decrease, okay, because you're getting more of the solid. Make sure you link back to solubility because that is what the question asked. So I hope that makes sense for that one. This next one is blast from the past. We learned this back in like one of the first lessons. If you put this reaction into ammonium nitrate, now the key thing here is you have to realize the silver, okay, the silver plus 2NH3 end up forming the silver complex ion. And if the silver complex ion is formed, what that actually means is it's a side reaction and it's a one-way reaction. So that means that these silver ions are going to be decreased. So the concentration of Ag plus is being decreased because the silver ions are reacting with the ammonia to form this complex. So that means that the equilibrium is going to shift to increase the concentration of silver ions. And if it shifts to increase the concentration of silver ions, the equilibrium is going to shift to the right. Okay, and if it shifts to the right, you're going to get more of the ions, okay, and less of the solid. Okay, so that means that you're going to get less AgCrO4 solid and solubility increases. So this discussion question is great because you have to, the first one talks about solubility decreasing and the second one talks about solubility increasing. Please note this equation here, Ag plus NH3 forms the complex. If you don't include that, you would not receive excellence for that question. Okay, so be very mindful. So here's my model answer. If this increases, it's going to shift to decrease the concentration, so shifts to the left, less silver chromate dissolves, solubility increases. Okay, and here silver ions form a complex with the NH3, removing them from the equilibrium. So this causes equilibrium to shift to the right to replace the lost Ag+, so more silver chromate dissolves, and we said that too in the equation. It's actually popped off the screen here, and I don't think, oh yep, I can move it down so you can see that the equation's been included, and that would get you an excellence. So I hope that makes sense. Final slide is just some helpful hints for common ion problems. Always use the concentration of the common ion in your problem. Okay, you must look at what the common ion is in the solution, if it's a 1-to-1 or 1-to-2, so be mindful of that. If the common ion is 1-to-2, then you need to double the concentration. When there is a common ion, the solubility will decrease. So I hope all of that's made sense. Here are the tasks. You've got to do SciPad pages 250 to 253, and there's a common ion worksheet, and I expect you to do 3 of the questions. Study Guide Activity 19C is optional for those who are struggling. Very well done, and I will see you next lesson for Ionic Product.